The most produced Allied tank of the Second World War had a design flaw that its own engineers documented in 1942. They wrote it down, they calculated it, they submitted it in a formal report to the United States Army Ordnance Department. The Army read the report. Production continued. Between 1942 and 1945, the United States built 49,243 M4 Sherman tanks. They sent them to North Africa, to Italy, to France, to the Pacific. They sent them faster than any factory in history had ever produced armor. And they sent them knowing something the crews who climbed inside them did not. A single penetrating round, not a catastrophic hit, just a penetrating round, could trigger a fuel-fed fireball inside the hull in under 3 seconds. The crews called it the Ronson, after the lighter. The tagline for the Ronson cigarette lighter at the time was, "Lights first time, every time." To understand why the Sherman existed, you have to understand the industrial situation the United States found itself in during 1940. America had no modern tank. Not really. The M2 medium tank, the Army's best vehicle at the start of the war, had armor thin enough that a standard German anti-tank rifle could penetrate it at combat range. When the Army watched German panzers demolish Allied forces in France during May and June of 1940, they understood immediately that they were years behind. The man assigned to close that gap was Major General Gladian Barnes of Army Ordnance. Barnes had a problem that was not primarily technical, it was industrial. The United States had to build a tank that American factories could produce at scale, using existing tooling, existing production lines, existing steel specifications in the shortest possible time. The best tank design in the world was useless if it took 4 years to tool up for. So the M4 Sherman was designed backward. Start with what the factories could produce, build the tank around that constraint. The hull was rolled homogeneous armor plate, welded seams, no casting. The engine was a modified aircraft radial because aircraft radials were already being manufactured in quantity. The gun was a 75 mm with a decent anti-armor capability at 1942 standards. On paper, in 1941, against what the Army expected to face, it was adequate. The problem was the ammunition. To feed the 75 mm gun quickly, engineers positioned the ready rounds in racks on either side of the lower hull, directly adjacent to the fuel tanks. The engineers knew this when they submitted the design. In a standard tank design, the ammunition storage question is a matter of geometry and trade-off. You need rounds near the gun for a fast rate of fire. You need the crew near the gun to load it. That places several highly explosive shells very close to several human beings in a metal box. Every tank design solves this problem differently. The Germans wet-stowed ammunition in the Panther, surrounding the rounds with a glycol water mixture that slowed the chain reaction if a round was struck. The British placed ammunition in armored bins below the turret floor. Neither solution was perfect. Both solutions were solutions. The Sherman's engineers chose speed of production over safety of storage. The ready rounds in the early M4 sat in unprotected sponson racks, horizontal bins built into the hull sides, just above the lower hull armor. They were positioned there because it was the most accessible location for a loader working fast in a confined space, and because it required no additional structural engineering. The problem was not that the rounds could be hit directly. Most penetrating rounds wouldn't reach them. The problem was the fuel. The Sherman used either a Ford GAA gasoline engine or a radial aircraft engine depending on the production variant. Both ran on high-octane gasoline. The fuel tanks were integrated into the lower hull structure, immediately below and adjacent to the sponson ammunition racks. When a penetrating round entered the hull, a German 75 mm Pak-40, a Panzerfaust, anything that got through, the resulting spall and heat didn't need to hit the ammunition directly. It hit the fuel. The fuel ignited, the fire reached the ammunition. The entire process, from penetration to catastrophic internal explosion, took between 2 and 4 seconds. That was not enough time for most crews to get out. In North Africa in 1942, American tankers reported a phenomenon that British tankers had already documented. A Sherman would be hit. There would be a brief pause, less than the time it takes to say the word, and then the entire vehicle would erupt. Not burn, erupt. The hatches would blow. The turret would lift. The British had a name for it that they'd been using since their own Shermans arrived in the desert: brewing up. By early 1943, the Army had formal after-action reports. The Army's response to the 1943 investigation findings was not a redesign. It was a calculation. The calculation went like this: a redesigned ammunition storage system, wet stowage, armored bins below the turret basket, and relocated fuel tanks would require retooling production lines. Retooling production lines at the rate the Sherman was then being built, roughly 2,000 vehicles per month, would cost somewhere between 3 and 6 months of output. 3 to 6 months of output meant somewhere between 6,000 and 12,000 fewer tanks reaching the front. The Army decided that was worse than the fire problem. This was not a secret decision made by one corrupt official. It was a documented institutional position worked out by the Army's production division, the Ordnance Department, and the Supply Command. Multiple people reviewed the trade-off. Multiple people signed off on it. The production schedule mattered more than the fix. There is a document in the U.S. National Archives, a 1943 Ordnance Department memo, that frames the Sherman fire vulnerability explicitly as a production management problem rather than an engineering problem. The language is careful, clinical. It describes the casualty rate from ammunition fires as an acceptable operational cost given current production commitments. The crews were not told. Meanwhile, the British, who were also operating Shermans by 1943, arrived at a different conclusion. The British 8th Army and the Royal Armoured Corps began lobbying for a modified storage arrangement almost immediately after their North Africa losses. By 1944, a portion of British-operated Shermans had their sponson ammunition removed entirely, reducing ready rounds but eliminating the fire risk from that source. It was an incomplete solution, but it was a solution their command structure was willing to implement at the expense of rate of fire. The American Army did not follow. The fix, when it finally came, arrived in late 1944 in the form of the wet stowage modification, the M4A1 76W, and subsequent variants, where the sponson racks were relocated below the turret ring and surrounded by a water glycol mixture. Testing showed that wet stowage reduced the probability of a penetrating hit following a penetrating hit by approximately 75%. The modification had been mechanically feasible since 1942. It entered production at scale in mid-1944. By the time it reached frontline units in significant numbers, the war in Europe was in its final stages. The gap between the engineers documented the problem and the fix reached the men was approximately 30 months. During those 30 months, the Army fielded the Sherman in North Africa, Sicily, Italy, and Normandy, the campaigns where unmodified Shermans bore the heaviest combat load. The casualty figures from crew fatalities inside Sherman fires have never been precisely isolated in official records. The Army did not track killed by vehicle fire as a separate category from killed in action. But post-war
Today, approximately 50 M4 Sherman tanks survive in running condition worldwide. Several hundred more exist as static displays in museums, from Bastogne to the Tank Museum at Bovington. You can walk around them. Read the plaques. The plaques describe production numbers, engine specifications, combat deployments. None of the plaques mention the 1943 memo. The dark part of this story is not that the Sherman had a flaw. Every weapon of the Second World War had flaws. The Tiger I's final drive failed so often that fewer than a third of its production fleet was operational at any given moment.